computer. There we go. Okay. So you have a test coming up next class. So let's first talk about tests next class. Here's how it goes. It opens on Thursday, that's tomorrow, 6/10/21 at 2:30 p.m. It closes Friday, 6/11/21 at 2:30 p.m. It's only one file. It's the typical 80 points. It's mostly multiple choice, but some FRQ mixed in there. FRQ will deal with the following items. So let's see, we have things in there, nuclear decays, like you did the alpha, beta, gamma decay, fission, fusion reactions, and the energy generated. So using E equals MC squared. I think that's kind of about it for the FRQ. It is more multiple choice than anything else. Any questions about the test? Okay. Well, let me tell you something fun. Oh wait, no, I am screen sharing. Cool, good. Okay. All right, let's hop to our notes for today. As I said, I'm just going to go through these, talk about them, and then you can ask any questions as you see fit. So the last topic of the entire year is the Big Bang Theory. And the Big Bang Theory, I'm sure most of you have heard about it, but you're probably not too familiar with it, what it does, et cetera, et cetera. So the Big Bang Theory simply says that the universe began as a singularity. It was infinitely small, dense, and hot. And for reasons we don't understand, gravity breaks away. So let me back up 1 second. All four of your natural forces, gravity, electromagnetism, strong nuclear, weak nuclear, are combined into one super force. For reasons we don't fully understand yet, gravity is the first one to break away. And we know it's gravity for two reasons. One is a mathematical model, and two is a theoretical model that would allow the universe to expand in a period we call inflation. It does this rapid expansion in the inflation period, and that only can happen if gravity breaks away. The long story short, laws like mass can't exceed the speed of light don't apply yet. But yeah, we're not going to get into that much heavy detail of the Big Bang Theory. We're going to actually focus on three important pieces of evidence and things that must be true in order for the Big Bang Theory to be true. So those three things are, if we start from singularity, the universe should be expanding. There should be an abundance of lighter elements compared to heavier elements, which you already know, number two. We implied it, but we never explicitly stated it when we talked about elements forming inside of stars. And then the universe should have a relatively uniform temperature. So we'll start with number one, expanding universe. So the idea first came out, should start saying 100 years ago, everybody thought the Milky Way was it. There was nothing beyond the Milky Way. There was a couple 100 billion stars. The Milky Way, that is existence. That is the whole universe. There is one galaxy you can see with your own eyes when you look up at the night sky. It's Andromeda. Don't get super excited. It looks like a star. It's just another bright, glowing dot in the night sky. If you had a hobby telescope, you might be able to make out that it's probably more like a star cluster. But if you had an advanced telescope, you find out that no, that's actually an entire galaxy. And Edwin Hubble discovered this in 1924, and he continued to search and found more and more and more galaxies. In fact, that's why the Hubble Space Telescope was named Hubble. It was named after him. And its job was to really find out, what do these galaxies look like? How far away are they? And any details about them that we could. So why do we care if the goal is to prove the universe is expanding? So now we have to go into Doppler effect. Which, if you remember, Doppler effect is the compression or expansion of waves that changes their frequency. So a police car with a siren blaring, heading towards you, those waves are being compressed, shorter waves, higher frequency, high pitched screeching sound. If light is doing this, so if light is moving towards you, it would move to shorter waves, higher frequencies, or what we call blue shifted, because you're moving towards the blues and indigos and violets. Now, in order for this to work, because you can't just grab a flashlight and move it back and forth in front of your face and watch it turn blue, red, blue, red, blue, red. The object moving has to be moving at an appreciable percentage of the speed of the wave. So a cop car going 60, 70 miles an hour is an appreciable percentage of the speed of sound. It's about 10 to 15% the speed of sound. So that's why we get Doppler. When you move your hand back and forth with the flashlight, you're nowhere near the speed of light. But galaxies do move at these speeds. And what we found is all but one galaxy is redshift. The one galaxy that's not, coincidentally, is Andromeda. It's going to collide with us. You don't have to worry, though. It won't kill you because you'll already be long dead before that happens. So, now, the two kind of interesting things come out of this. Not only is everything redshifted to us, every galaxy is moving away from every other galaxy. So a redshift is observed by all galaxies, tells us they're moving away not just from us, but from each other as well. So the universe is expanding. Not only is it expanding, but it's accelerating. So the rate at which these things are moving away from each other is also increasing. That's the evidence that dark energy exists. Now, dark energy is really just our way of humbly saying that we don't know. We're ignorant. We don't understand what it is. We know it's got to exist in some form. We just really don't know what it is. Yeah. So this gets a little bit complicated when we talk about the universe expanding. Stars are not necessarily getting farther apart from each other. The stars in our galaxy are galaxies staying pretty much the same size. What's happening is more physical space is being created in between galaxies. The universe is literally creating the dimensions of space that you live in. It sounds a little bit strange. The best analogy I got for you is let's take a two-dimensional object and expand it in a three-dimensional world. So if you take a balloon, now you say balloon's three-dimensional. Think about the surface of the balloon. It's a surface area, and the area is two-dimensional. If I blow into the balloon, it gets a little bit bigger. Now, if I blow into the balloon again, it gets even bigger. I've expanded that two-dimensional thing, the surface area, in my three-dimensional world. So trying to visualize that for the expansion of the universe is a good analogy, but still kind of difficult to wrap your mind around. How do you expand something that's at least four-dimensional? All right, questions on one? Okay. Let's move into two. So two. Let's see. So two is the abundance of light elements over heavy elements in our universe, and we see that pretty clearly. Stars, all stars take hydrogen and fuse it into helium. High mass stars take helium, fuse it into iron. And the only time something above iron gets made is inside of a supernova, which is relatively rare. Now, our universe is about 74% hydrogen, 24% helium, and then we would say it's about 2% all else. So we've already kind of discussed what the how the elements are made and how lighter elements are favored. So I don't really want to spend too much time on number 2. Do you have any questions about it, or am I free to move on? Okay. Number 3, it's another little bit of a complex one. Number 3 was actually being looked for but discovered by accident. Here's the idea. A couple of physicists said, all right, if Big Bang's real, then the universe should be mostly evenly distributed and thus have a uniform temperature. Now, anybody who's ever detonated a firework or a firecracker, just watch anything explode, you know that, yeah, the debris gets pretty uniformly blown around, but it's not unusual to see that there's slight variations in how matter is scattered. We would expect something similar from the Big Bang, which is why we would still see star formation. One pocket of gas happens to have a little bit more mass than another, gravity wins. But the temperature should be pretty uniform throughout. So the proof of this was something that these two physicists could not figure out. Now, 2 astronomers come along and they're trying to do a whole completely different experiment with a radio telescope. They want to map out radio frequency radiation throughout the universe. Now, what they found is, as they pointed their radio telescopes to the sky, they got static. It's kind of like if you put your car radio station in between 2 stations and you get this weird fuzzy white noise static. They were getting static everywhere they pointed. It didn't matter if they waited, oh, there's the bell. If they waited until the changing of seasons, so the Earth had made, say, a quarter or a half a revolution around the sun, then looked at that different sky, it doesn't matter if they pointed it at the sky during the day or at the sky during the night. Remember, you're looking for radio waves. You're not really concerned about it being bright outside. No matter what happened or wherever they pointed it, they got the static. And they had no idea why. They had a whole bunch of different theories, and all of them were definitely wrong. Somehow these 2 groups, the physicists and the astronomers, ended up getting together, and what the physicists realized is the astronomers found what the physicists were looking for. Here's the idea. Universe is born, it's way too hot for electrons to bond with protons. It's all a plasma. Solid, liquid, gas, plasma. It's plasma. Plasma is the electrons are not bound to the protons like they are in a typical atom. They're not bound because it's too hot, which means they're free electrons. These free electrons emit light. They also absorb light. So we predict that any light emitted from the universe, the early universe, is not present, because as soon as it got emitted by one electron, it got absorbed by another, and re-emitted, absorbed, re-emitted, absorbed. Eventually, what would happen is the universe would cool down. And when it does cool down, the electrons would naturally be attracted to the protons, enter into an electron cloud and orbit. Now, we never talked about this, but one of the things on the atom and the electron perspective is there's what's known as ground state, or the lowest energy level for the electron. Electrons naturally want to go to the lowest energy level. So once the universe cools enough, and it cools uniformly, electron gets bound with proton, drops, and when it drops to the lower energy level, it emits light. Now, not visible light you see with your eyes, but microwave radiation. Microwave is a part of the radio spectrum. So what these astronomers were doing with their radio telescope, wherever they looked, they were picking up on these microwaves. Because at one point in the universe, the whole universe was scorching hot. It drops below a certain threshold in temperature, then boom, microwaves shot everywhere. And they've been traveling for 13 plus billion years. We call this the cosmic microwave background radiation. It is everywhere. And it tells us the universe did disperse itself evenly, And it is a constant uniform temp throughout, and it's about 3 Kelvin. So first piece of evidence, the universe should be expanding. It is expanding, it's actually accelerating. Second, we should have more lighter elements than heavy, and we definitely do. 98% of the universe is either element number 1 or number 2. Third thing, there should be a uniform temperature throughout. The cosmic microwave background radiation tells us the universe is evenly distributed and is at a pretty steady 3 kelvins. That doesn't mean that you're 3 kelvins when you're next to a star. It's talking about interstellar space. Go out to Pluto. All right, very last thing for the entire year. How we got from, well, the beginning to now. So 13.7 billion years ago is Big Bang. 200,000 years later, the CMB is present. That's when we can actually start seeing things. For the first several billion years, it's all high mass stars dominating the universe. They're making all the elements that we see today. I already see a bunch of typos in these notes. I'm not an English teacher, don't make fun of me. So generation after generation of high mass star, high mass star, high mass star, you start to get slightly smaller stars and therefore slightly smaller nebulas over time. About 5 billion years ago, in a nebula that remained from a supernova, the sun is born along with about 15 to 20 other stars. About 4.4 billion years after 4.4 billion years ago, it took almost more than half a billion years for the accretion disk, which was the remains of the solar system, what did not become the sun, to start coalescing and combining together and forming planets. Earth is finally forming to the point where it can begin to cool down. The oldest rocks we found are about 4.4 billion years old. The oldest fossils we found are about 3.8 billion years old. So currently, our best knowledge, life first appears on Earth 3.8 million years ago. How did it get here? Where did it come from? Why is it here? Don't know, and don't know. So it's a great mystery. For the first 3 billion years, though, life is pretty boring. In single-celled organisms, there's no oxygen. But suddenly an oxygen-producing life form, which takes sunlight and conducts photosynthesis, which results in the carbon dioxide molecule being broken up into carbon and oxygen, the atmosphere is flooded with oxygen. This causes a mass extinction and most things die off. But that mass extinction paves way for oxygen-based life forms. And the reason why oxygen is such a big deal is it allows for respiration, which you get very complex life. This happened about 450 million years ago. We call it the Cambrian explosion. It was the most diverse life has ever been on Earth. The majority of animals are already extinct, and most of them went extinct when the Cambrian explosion came to an end. A whole bunch of stuff happens between now and then. Species rise and fall, rise and fall, rise and fall. 65 million years ago, dinosaurs fell to an asteroid. Mammals began to dominate because we were tiny little furry rodents that could hide and survive the nuclear winter that came from the asteroid's fallout. We did survive, and those mammals evolved and evolved and evolved, and about 100,000 years ago, Homo sapiens show up. We're not alone as humanoids. There are other humanoids as well. Neanderthals are probably the most common one that people know. Why? I don't know. That's the one that people know. But it was not just humans and Neanderthals. In fact, humans and Neanderthals did intermate. We do know that. There's Neanderthal DNA in human beings right now. Moral of the story, we spend tens of thousands of years doing nothing. Okay. And about 6,000 years ago, civilizations first start to appear. Idea is pretty simple. Those plants that you're eating, if you take the seeds from them and you purposefully scatter them on the ground, you no longer have to be nomadic. You don't have to be a hunter-gatherer. You just sit there and wait, and then the food grows. Civilizations began appearing near rivers, particularly rivers that flood, because it replenishes the soil every year. 17 years ago, your parents end up making you. roughly 17 years ago. And today you're here, and everything other than the hydrogen in your body is forged in a sun or in a star or a supernova. Let me stop this.